Okay, so here's section 3.10 on hypothesis testing. So what we need to do at the beginning is to make sure that we understand the data that we're working with. One of the first things that we did when we started statistics was to look at the two different types of data. And this is, one of the reasons why we broke that down, right? We could see from the beginning that the type of math that we can do is different for numeric and non-numeric data. Okay. So it's going to be important to make that distinction. However, we're going to be focusing just on non-numeric data for this hypothesis testing portion. Okay, we just need to make sure that we can correctly identify when we have the right data. Okay. The other thing that we want to talk about before we get started in an actual problem is to understand all of the stuff that we can do with the tools that we have available. So inferential statistics is primarily concerned with two main things. One is estimating, okay, which is what we were doing with confidence intervals. And the other thing is called hypothesis testing, which we're going to do today. And it builds off of that idea of estimation. Okay, so in section 3.9, we learned how to compute and interpret point and interval estimates for a population proportion P. So in this section, what we're going to do is we're going to use those intervals to test a hypothesis about the value for P. So we're going to get a little bit more practice with computing confidence intervals, and then we're going to go one step further and use that confidence interval to answer a question. Okay, so here's our types of data. When we have qualitative data, remember that's the non-numeric, then we have n indicates our sample size. Okay. X is going to be a random variable that counts how many yeses that we have. And p hat is going to be the variable that gives us the proportion or percent of yeses. Okay. When we have quantitative data or numeric data, okay, n is the sample size again. X bar is the sample mean. And S is the sample standard deviation. Okay, so this is like the different information that we can get from a sample based on the type of data. When we have non-numeric data, we're going to use that sample information to answer questions about P. So this is going to be the percentage of people that would say yes in the whole population if they were asked the question. Okay. If we had numeric data, we would be using our sample information to answer questions about mu, which is the population mean. Okay. And one of the things, and we'll talk about this when we get to a specific example, but something to keep in mind is when we talk about this population parameter P, and likewise when we talk about the population mean mu, those are values that we will not ever get to know the real value of. Okay, it's a number that exists, but we just don't know it. Nobody knows it. Okay, and the only way to get to know it would be to do a complete census, right? To ask everybody the question. And in reality, even that doesn't tell you everybody's response. what we do is we say this is a number that exists and we would like to know it, so we want to get the best chance that we can at knowing what it is. All right, so we'll look at an example and I'll talk about that more. So let's look at how we can use a confidence interval to help us answer a question. So here's some example of some sample data, right? We can collect sample data, and one of the things that we can do is we can see if something has changed from before. For example, let's say it's claimed that 15% of the population smokes. You want to see if that's actually true, or if maybe it's changed since then, right? Maybe that was an old study or something like that, and you want to see if it needs updating. So you get a sample, and you find in your sample that 20% of your sample, your random sample of people, is smokers. Okay, what we need to do is figure out, does this mean that there are more smokers now than there were before? Or is this just some of the random fluctuation that happens when we take a sample, right? Because we know every sample will differ a little bit from other samples and will differ from the population. So is this just some of that normal random fluctuation, or does it indicate that it actually more than 15% of the population smokes? Okay, so that's a question that we would want to answer. Here's another one. A company claims that 40% of Americans use their brand. Okay, you take a sample and you find that in your sample, 38% of people use that brand. Okay, again, is this just a random sample fluctuation, or is this evidence that the actual percentage of people who use that brand is less than 40%? Okay, so intuitively, if the percentages are very close, right? If somebody claims it's 40% and you get a sample and it says 38%, then you might be more inclined to say, oh, that seems like it's a natural fluctuation, right? If instead in your sample you got like 5%, then you would probably be more inclined to say, I think that their 40% is wrong. I don't think that really that many people use that product, okay, or their brand. Okay. That's kind of an intuitive idea. What we want to do is have a mathematical tool for answering that question and having like a reason why we answer that, right? Instead of just, I think it's this, okay? So here are the tools that we can use, right? So there's a few different ways that we can answer this. There's the classical approach, right? That, we're not really going to go to. That's hypothesis testing before we had computers, okay? We have something called a p-value approach, and we have a confidence interval approach, okay? And what we're going to do, because we just learned confidence intervals, is we're going to use this confidence interval approach. Okay, but there are other ways of going about the same thing in statistics. And they really all rely on like the same math at the backbone, but they all feel very different. Okay, so it's like different ways of solving a problem. All right, so what we're going to do is we're going to look at our sample and take a confidence interval. And if the claimed value of P is not inside the interval, right? So if I take my whole confidence interval and my whole interval is above P, okay? So maybe if maybe a number line will help, okay? So let's suppose that I claim that 15% of people smoke, okay? And you take a confidence interval, right? You take a sample, and in your sample, the confidence interval is completely above that 15%. Maybe your confidence interval goes from 18% to 22%, right? With 20% right in the middle. Okay. Then in that confidence interval, you would say that you're 95% confident that the actual proportion P is between 18 and 22%. Okay. So that gives us good evidence that it's not really 15%. 15% is wrong. The actual number is higher. We don't know exactly what it is. Our sample tells us it's 20, but we know that our sample isn't exactly right. It's not exactly the same as the population. but it gives us strong evidence that it's, somewhere in this 18 to 22% range. So that gives us something to base our claim off of, right? Okay. If the whole interval is below the claimed value of p, then there's significant evidence that the parameter is smaller, right? That's the same idea except on the other side, right? If I look at, say, here's my 15%. If you were to take a confidence interval and it's over here, right? Maybe your confidence interval goes from 8% to 12%, okay? Then that gives us evidence that the actual value of p is smaller than that 15%. Okay. Now, what happens if the claimed value is inside the interval? What happens if somebody says, I think 15% of the population smokes. You take a sample, and in your sample it's 20%, but you have a very big margin of error. So your confidence interval goes from, say, 13% to 27%. Okay, so I can see that the claimed p is right inside. Well, if I'm 95% confident that the actual value of p is between 13 and 27, and somebody else says, I think it's 15, we're not contradicting each other, right? We don't have any evidence to say that that value is wrong. So there's no way to say that the 15 is wrong, okay? But there's also no way to say that the 20 is wrong, or 21 is wrong, or 19 is wrong. So what that's really doing is it's saying we don't really have enough evidence to say something different, okay? And that's something that we have to be a little bit careful about. We don't always get a definitive conclusion when we do statistics like this, right? If somebody claims that it's 15 and I don't have evidence to contradict them, I can't say that they're wrong, but I also can't say that they're right because my evidence doesn't contradict any of the values in this confidence interval. Okay. All right, so we're going to talk about that more when we do an example. So let's go ahead and look at an example. Okay, so let's say that it's claimed that 15% of Harper students smoke. We take some data and we collect the data on a sample, and we construct a 95% confidence interval. Okay, so we're going to skip the whole process of creating a confidence interval. Let's just look at what happens if I have that already done. And we've computed this confidence interval. The confidence interval goes from 17.5% to 22.5%. Okay. So first of all, what if I'm asked, what is the value of p hat? Remember that p hat is the sample proportion. Okay. I know that the sample proportion is going to be the very middle of my confidence interval. Okay. So if I don't know, or I forgot my p hat, but I can see my confidence interval, I know that this is going to be halfway between 17.5 and 22.5. So what I can do is I can take those two numbers and average them. I can take 17.5 plus 22.5 and divide by 2. So I get 20. Okay, so p hat is 20%. Now I want to be careful not to lose my percentages because really p hat I know is a number that's smaller than 1. It's 0.2. As a percent, it's 20%. So I can work with percentages as long as I'm not multiplying. I can work with them as percents, and that's fine as long as I don't lose my percent. Okay. Alternatively, you could have converted these to decimals first. I could have had 0.175, 0.225, averaged those together and got 0.20. And I could say, okay, p hat is 0.20. And that works fine too. Okay. All right, now, what can I say about this, right? If I look at that 20%, that 20% is bigger than the 15%. Okay. So p hat is 20%, which is more than 15%. Okay. But that alone isn't enough to make a conclusion. Okay. Because of, I can't tell if that's different because of the natural randomness in taking a sample, or if it's because it's actually wrong. Okay. So now we're going to look at the confidence interval. So what I'm going to do is I'm going to make a little, line graph here with all of my information. Okay. So we have this claimed value of p that's 15%. Okay. So I'm going to plot that here, right? So here's p is 15%. Okay. Then I have my confidence interval that goes from 17.5% up to 22.5%, where p hat is in the middle here. Okay. All right, now I can see that my entire confidence interval is bigger than the p hat. Okay, so the whole range of values that I feel confident that p is in, right? Well, if somebody claims a p that's not in there, then I have evidence that they are wrong. Okay, so what can I conclude? Since the entire confidence interval is above the claimed value, okay, then we have statistically significant evidence that p is bigger than 15%. Okay, that's what we can conclude. All right, now let's look at another example. This time the p is going to be inside the confidence interval, right? So little spoilers here. All right, let's say that it's claimed that 12% of the US population is left-handed. We collect some data and compute a confidence interval. And again, we're going to skip over making a confidence interval for a minute and just look at what do we do with it. So once again, we can start off by saying, if I'm given a confidence interval, what's the value of p hat? Now, if I'm computing a confidence interval in my calculator, it tells me the p hat. But again, I just want to go back over and stress this relationship. P hat is always going to be in the dead center. So if I want to find the p hat from the confidence interval, I can just average those two values. So p hat is going to be the 9%. This time I'll write it as a decimal. And the 13%, and then I average them. So add them and divide by 2. So when I add those, I get 0.22. And when I divide by 2, I get 0.11. Okay, so I can say that p hat equals 0.11 or 11%. Okay. All right, let's look at plotting everything on a graph here. My confidence interval, well, that's sort of already written down, so I'll just go ahead and label that. Okay. So that goes from 9% to 13%. And I know that in the dead center here is p hat, and that is 11%. Okay. Now, if I want to plot the 12%, I can say, well, that's bigger than 11, but not as much as 13. Okay. Okay. Here I can see that the claimed value is inside my confidence interval. And that's a confidence interval says we're confident that it's going to be somewhere in this interval. It doesn't say that it's going to be 11%. It says it's going to be somewhere in this interval. So if a claimed value is in this interval, then we don't have any reason to suspect they're wrong. Now, the problem is we also can't conclude that this person is right, because we have just as much evidence that somebody who says 10% would be right. And it doesn't make sense to say that 10% is right and 12% is also right. They can't both be right. Okay. So what it is that when we create a confidence interval, we have some sort of, we're doing statistics, we have a level of uncertainty. So we can't say that one specific number is absolutely correct. Okay. We can say that certain numbers are incorrect, but we can't say that this number is correct. So since the claimed value, or P, was 12%, is in the interval, then there is not evidence that P has changed. Okay. So notice that saying that we don't have evidence that they're wrong is not the same thing as saying that we have evidence that they are right. Okay. So we don't have evidence that P equals 12% is wrong. Okay. So that is not the same as having evidence that they are right. Okay. All right. Let's go through another example. This time what we're going to do is we're going to go through the entire process. So instead of being given a confidence interval, we're going to go through the process from the beginning, and included in that is constructing the confidence interval. Okay, so let's say that it is claimed that 16% of peanut M&Ms are green in color. In a random sample of 5,000 peanut M&Ms, we find 720 that were green. And we want to use a 99% confidence interval to test the claim that 16% of peanut M&Ms are green. Okay, so the first thing that we're going to do is create a confidence interval. And what we're going to do is highlight, or have listed out the steps for doing that. So I'm going to walk you through the steps, but it's already written down. So the first thing that we do is identify the parameter that we're testing. Okay, so we want to write this out. We want to say, okay, P is the percentage of all peanut M&Ms that are green. Okay, X is the number of green M&Ms in our sample, right? And N is the sample size, 5,000. Okay. The next step is to double check the assumptions. Okay, so remember we had those, well, we had 2 bullet points, but it's really 3 assumptions, right? One of them is that NP, which is the same as saying the number of yeses, or the number of green M&Ms, is bigger than 10. Okay, so I have 720 of my M&Ms that are green. That's bigger than 10. Okay, then I look at how many M&Ms are not green. Okay, so we take N minus X. Okay, so what we would do is we would say, okay, take 5,000 and subtract the 720 green, and I'm left with 4,280 that are not green. And that's bigger than 10. Okay, check, check. The last thing we do is we look at the population size. And I don't know how many there are. I don't know how many green M&Ms they are. What we do is we say it's not given. We need it to be bigger than 10,000. Okay, so what we can do is we can just say we will assume that there are more than 10,000 peanut M&Ms in the world. Okay, and we don't need these to all like exist even at the same time. So like if you're eating some, that's not a problem. That's not hurting our population here. All right, after we verify the assumptions, now we want to name the test that we're using. Okay, we're using this one proportion z interval. Okay, this name the test should be easy because we're really only covering one test in this class. All right, but we want to make sure that we're being clear and breaking this up into steps. So now let's go ahead and create the confidence interval. So we're going to use our calculator. If you have an TI-83, that's fine too. If you have a different calculator, then make sure you talk to me and see if we can figure out how to get it to create confidence intervals for you. But what we're going to do is we're going to use this one proportion z interval. Okay, so let me walk you through doing that on your calculator. So I'm going to press stat. I go over to tests, and I go down, all the way down here to one prop z int. Okay, be careful. There's a lot of things that start with one prop. Okay, make sure you get the one prop z int. It should be under the letter A. Okay, it's prompting us for the x. Well, we wrote down the x in the step above, right? That was 720. That's the number of green M&Ms. Okay, n is the sample size. We wrote that down too. We took a sample of 5,000. And C level is the confidence level. We want to create a 99% confidence interval. Write that 99% though as a decimal, so 0.99. And then we hit calculate. And that gives us our interval. Okay, so the calculator is going to give me 0.13121. Comma 0.15679. Okay. And it gives me p hat is 0.144. Okay. What I'm going to do when I write this down is two things. I wrote down the decimals, but we're gonna do two things with this. First, we're gonna convert that to a percentage. So I convert decimals to a percentage by moving the decimal over two places. So this 0.13121 would be 13.121. And then we'll just round to one decimal place. Okay, and in a problem you'd be told how much to round to, but here we're just gonna round to one decimal place. Okay, so we move the decimal over two places and then we round it, so we get 13.1%. Over here, I move the decimal over, so I have 15.679. That will round to 16.7, or sorry, 15.7%. Okay. Over here, for the p hat, if I move the decimal over twice, I am at I'm at one decimal place. So that I don't need to do any rounding, so I'll just have the 14.4%. Okay. So then we can write our conclusion, right? So our conclusion is we are 99% confident that the proportion of all peanut M&Ms that are green is between 13.1% and 15.7%. Okay, so we could write that. All right, now we're going to get into the next step where we're going to use our confidence interval to actually test this claim. So what we're going to do is make a little plot, a little line graph here. And we're going to say, okay, I'm going to start by putting in my confidence interval. That goes from 13.1% to 15.7%. Okay, the p-hat is always in the dead center. And that's 14.4%. And then what I need to do is I need to plot the p that was claimed, 16%. And I can see that that's bigger than 15.7. That's going to be over here. Okay. So what can we conclude? Since the entire confidence interval is below claimed value of p, there is significant evidence that p is, well, I'll say that the parameter p is smaller than they claimed. Okay. Or another way to say that in context here, what we could say is we have evidence that less than 16% of M&Ms, of peanut M&Ms, are green. So since the entire confidence interval is below 16%, we have statistical evidence that less than 16% of all peanut M&Ms are green. Okay. One of the things that I really want to emphasize here, and I wrote it in caps, is our conclusion is about the whole population, right? In this case, all M&Ms. We're not writing a conclusion about the 5,000 M&Ms. We already looked at all of those. We know exactly how many green M&Ms there are. We don't need to do any crazy computations other than just counting them, right? The reason that we're doing all of this work is because we're talking about all M&Ms, not just those 5,000, right? And that's the point of statistics. We don't care about the sample. We're using the sample as information to tell us about the whole population, right? That's the idea. Okay, that's the whole process that we're going through. So that's it for today.